Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a cubic equation with complex solutions. And I'll be presenting two methods, and let's start with the first one. We have z cubed minus z squared minus z equals 1/3. Can you guess the solution at this point? Probably not, because that will be pretty hard, right? So for my first method, I'd like to use what is called the cubic formula. Now, how does the cubic formula work? We start by substituting something for z, and our goal is to get rid of z squared. So let's replace z with w plus 1/3. Let me tell you where the 1/3 comes from. The 3 comes from the degree of this polynomial, and the 1, the positive 1, comes from the opposite of the coefficient of z squared, which is -1, right? So its opposite would be +1. Great, so let's go ahead and substitute that. Without further ado, I'm gonna tell you what that's gonna turn into. You can definitely do it pretty easy. Just substitute and simplify by combining like terms. Now, after you do all the work, expand the cubes and the squares and everything else, you're going to end up with the following equation: w cubed minus 4/3w equals 17/27. Notice that there is no square term or quadratic term in this expression. So this is called a depressed cubic, which is missing one of its terms, and that's the whole idea behind solving this equation. Because now we're going to use substitution, and if you kind of consider the following identity, a plus b cubed minus 3ab times a plus b equals a cubed plus b cubed, you notice that in this equation, by way of substituting w for a plus b, we get a cubic equation for w, which is what we have. Therefore, by comparing the coefficients here and here, we get the following: -3ab equals -4/3, which implies ab is equal to 4/9. And by setting the constants equal to each other, that implies a cubed plus b cubed is equal to 17/27. Now we want to come up with a system that we can solve, and here I would go ahead and just cube both sides, and that would give me a cubed b cubed equals 64/729, which is 9 cubed, right? So this is going to be my system. And how do I solve this system? By way of substitution, or I guess there's no way to eliminate, but you can use substitution. Let's go ahead and isolate b cubed from the first equation. We can write it as 17/27 minus a cubed, and then go ahead and plug that in here. Replace b cubed with 17/27 minus a cubed, and that equals 64/729, right? Awesome. If you distribute and put everything on the same side, you're going to get the following equation, which looks hectic, whatever you want to call that, right? But it can actually be turned into a quadratic equation easily if you replace a cubed with something like c. If you do that, this is going to become c squared, and you're going to end up with a quadratic equation. And to solve this quadratic equation, all you need is a quadratic formula. Even though there's no hexic formula, a quadratic formula actually exists. So you can use it to solve. But again, that's pretty painful because it's not going to end there. You're going to find c, and then from finding c, after finding it, you're going to cube root c. That's going to give you a and b. And then you kind of have to add them, a plus b. That's going to give you a w, and from the w, you're going to have to find z by using z equals w plus 1/3. But guess what? That's only going to be a single value of z, because using this method only gives you one solution. And then, of course, once you find the solution to the cubic, you can find the other solutions. Let me quickly demonstrate with another equation how this can be done. Suppose you have something like this. Let's say we do know that this equation has a solution at 1. I mean, that's kind of obvious, right? Z equals 1 is a solution. How do you find the other ones? You can go ahead and do long division with this, divide this by z minus 1, and find the answer. Or you can kind of take this and manipulate this in such a way that it'll be divisible by z minus 1, kind of like in pairs. And we can kind of do that z cubed minus z squared plus z squared minus z plus 2z, or not 2z, minus 2 equals 0. And now by factoring by grouping, we can get z squared plus z plus 2 multiplied by z minus 1 equals 0. We already knew z equals 1 is the solution. The other solutions come from here. And if you look at this equation, you're actually going to get non-real complex solutions from here, because that's going to be negative b plus minus the square root of b squared minus 4ac. That's going to give you square root of 7i divided by 2. But finding the other solutions by way of factoring is fairly easy, because all you have to do is divide and eliminate the linear factor, right? So that's fairly easy to do, but what is that particular solution here, and is that going to be easy to do? I'm going to leave that as an exercise, okay? Don't hate me for that, because this is really good practice, and you should definitely practice it if you want to get good at algebra, or for some reason you want to, just get smarter, use your brains, right? For algebra or math in general, you don't really need a good reason like, oh, I'm learning math because of this. No, you can just learn math for the sake of math, because math is beautiful, math is love. Anyways, let's go ahead and talk about the second method, because the second method is actually pretty exciting in my opinion. So I'm going to start by manipulating this equation. What do I mean by that is you can add the same number to both sides, you can multiply both sides, so on and so forth. In this case, I want to multiply both sides by 3, because that gives me a well-known pattern. You'll see in a little bit why. When I multiply the right-hand side by 3, I get 3z squared plus 3z plus 1, which is actually a part of, did you recognize it? Okay, I'm going to spoil the surprise. Ready? Pause the video if you don't want to hear it, but basically this is part of a perfect cube, right? Because if you add, and I'm going to go ahead and rewrite this so we can have some room. So now I'm going to add z cubed to both sides, because there's a good reason for that. This now becomes a perfect cube, and that's just perfect. So this becomes 4z cubed, and this becomes z plus 1 cubed. So we have cubes on both sides. Even though 4 is not a perfect cube, we can make it work, okay? You don't need to multiply both sides by 2 to make it a perfect cube, because that's going to mess up the right-hand side. So here's what we're going to do. Instead of cube root on both sides, I want to put the z's together. So kind of like divide by z cubed and put the variables on the left. You can kind of switch sides. And then write this as a single expression, a rational expression cubed. We can do that, right? Properties of exponents allow us. Now, we will solve this problem. But remember, this channel is all about complex numbers, so we're going to find not just one, but 3 solutions, because a complex number has 3 cube roots. Let's go ahead and quickly find them. And to be able to find it, actually, you're going to write 4 in polar form. To do that, we're going to use the complexified version of 1, which is, by the way, 4 times 1 is 4, right? So we're going to use 2e to the power 2 pi ni, because that's exactly 1, right, in the complex world. Now, if you cube root both sides, this is what's going to happen. You're going to be getting z plus 1 over z. And then this is now a real r, or ration, whatever, modulus. You can just write it at the cube root. Initially, you probably would need to use to the power 1/3. But anyways, here you can just divide by 3 to get the cube root. And now we can talk about different solutions here, because if n is equal to 0, let's start with that easiest case, right? Of course, you're going to get cube root of 4 multiplied by e to the power 0, which is 1. So from here we can find z plus 1 equals cube root of 4 times z. And I put the z's on the same side and kind of factor out the z. Cube root of 4 minus 1. Oh, I can't write a 2. I can't write a 4. A 3. Whatever. So yeah. And this equals z plus, z. It's equal to 1. And now we can go ahead and divide both sides by cube root of 4 plus 1. Cube root of 4 minus 1, sorry. And that's going to give us 1 over cube root of 4 minus 1. So this is one of the values of z. And of course, we can find the other solutions as well. Let me just quickly show you how that can be done. And the rest is, again, going to be yours. So instead of using n equals 0, we could use n equals 1. And that's going to give us z plus 1 over z equals the cube root of 4 multiplied by e to the power 2 pi I over 3. You just got to remember, in polar form, thanks to Euler, this can be written as cosine of 2 pi over 3 plus I times sine of 2 pi over 3. 2 pi over 3 is 120 degrees, and its cosine is going to be negative 1/2 as far as I remember, and the sine would be root 3 over 2. It's positive because it's in the second quadrant. Go ahead and plug this in here, cube root, cross multiply, and n equals 2 will give you the other solution, so on and so forth. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.